What's up, physics? Welcome back to the Dirt Bike Shed. Today we're going to talk about gravity. We're going to talk about not just acceleration with gravity like we did yesterday, but we're going to talk about planets and celestial bodies and the forces they exert on each other. Now, what you're watching here is a little demo that a guy does, and he's got a sheet of elastic fiber, it's like spandex, and he's got it stretched across the frame for a table. Now, the name of this video, if you want to check it out yourself, is called Gravity Visualized. Gravity Visualized. And he's showing you, he's got there, that's empty space, and now he put an object on it. And see how it warped the shape? That's what the Earth and Sun and massive celestial bodies are doing to space. They're literally warping the fabric of space-time. Check this out. He puts another object on it, and the two move together. Bam. That is how gravity works, okay? That's the long and the short of it. Isaac Newton didn't quite realize this when he developed his formula that we're going to use today, but Einstein figured it out. Now, you'll see here he's put a heavier object on the spandex, and it warped it more, and now he's going to roll some marbles, and you're going to see these things orbit. Check that guy out right there. It is orbiting. That is what the planets are doing to the sun. That is what gravity is. That is the best example that I've seen of how it works. All right? So let's take a look at some math here. Now, of course, the formula we're going to use today is this. Force of gravity is equal to the gravitational constant times the mass of one body times the mass of the other body divided by the distance between them squared. And you're like, Mr. Perkins, why isn't there a D there instead of an R? All right, let's say this is the fiery hot sun right here, okay? Now, the distance between the Earth and the sun is pretty far, so there's the Earth. Now, what's the Earth doing? Here's the distance, right? What's the Earth doing? It's moving that way with a sideways velocity. And because space-time is warped, just like that sheet we just saw, the Earth is going in a circle around. So now that distance, now doesn't it make sense? We call that a radius, right? Doesn't that make sense? Because the distance between you and a body you're orbiting is actually the radius. Now that we've cleared that up, let's do a little math here, and let's find out how hard do the Earth and sun pull on each other. The Earth and the sun. With what amount of force in newtons are they pulling on each other? Well, we can figure that out pretty quickly. Force of gravity is equal to G. Now we know that this letter G stands for, every time, 6.67 times 10 to the negative 11th. Now we need to know the mass of the sun. All right, the mass of the sun is 1.99 times 10 to the 30th kilograms. I'm going to give you a chart. Don't worry, you don't have to memorize that. And then the mass of the Earth, let me make my line, keep going over it. The mass of the Earth, you may remember from yesterday's lesson, is 5.98 times 10 to the 24th kilograms. Now, let's find the distance between these two. The distance between these two can be found on our useful planetary data. I like that. I'm going to post this with the assignment under gravity planet mass chart, okay? All right. So the distance from the sun to the Earth, see, here's the Earth. We're going to go over here. Mean distance from the sun is 1.496 times 10 to the 11th meters. So I'm going to call that 1.5, okay? So the distance in meters from us to the sun, and this is an average, is 1.5 times 10 to the 11th meters. So this whole answer will work out to be the force with which the sun and the Earth are pulling on each other. The Newton force that keeps the Earth in orbit. Let's do the math together. I'm going to show it to you on the calculator. Ready? You can watch me type it in if there's enough light. Okay? I turned the light on, hoping that would help. Here we go. 6.67 EE11 negative times 1.99 EE30 times 5.98 EE24 equals, divided by 1.5 EE11 squared equals, I get 3.5 times 10 to the 22nd newtons. So I get 3.5 times 10 to the 22nd newtons. Okay? That's how easy this is. Now, I've seen questions saying, how hard does the sun pull on the earth? 3.5 times 10 to the 22nd newtons. How hard does the earth pull on the sun? 3.5 times 10 to the 22nd newtons. All right? So here's what we're going to do. I'm going to give you some problems, and you are going to try to figure them out. Okay? And you're going to need to use the numbers from the chart I give you. And here are the problems. Number 1, how hard or with what force, okay, does the sun pull on Mercury? Okay? How hard does the sun pull on Mercury? You're going to use F of G equals G, M1, M2, R squared. You're going to put the sun's mass here, Mercury's mass here, the distance from Mercury from the sun right here, and solve the problem. Okay? There's the formula filled out. You'll see the mass of the sun here, mass of Mercury here, the distance from the sun. And the answer you got should be newtons. Question number 2. What is the force? What force does the sun place on Jupiter in its orbit? Or Jupiter also exerts that force on the sun. So we're talking about the force between the sun and Jupiter. Use this formula. Once again, F of G equals G, M1, that's the sun, M2, that's Jupiter, R squared, that's the distance between the two. You should have gotten that for your answer. What force exists between the sun and Pluto? I'm not going to give you the formula again because you know what you're doing. The answer's coming up. You should have gotten 4.83 times 10 to the 17th newtons. What is the force of gravity between the sun and Venus? What is the force of gravity between the sun and Venus? I used my chart. I got 5.55 times 10 to the 22nd newtons. We got one more problem. What force in newtons exists between the sun and Saturn? What is the force of gravity? Don't forget, I'm going to show you the formula again. M1, M2, R squared. This is the mass of the sun. This is the mass of Saturn. This is the distance between them squared. And that answer is 3.69 times 10 to the 22nd newtons. I hope this helps you. You're going to try to solve this on an Ed puzzle. Good luck.